October 2025, under the thin sky of Mars, a silent flash tore across the starscape, moving faster than anything Perseverance had ever seen. 60 kilometers per second. That's not just fast, that's interstellar fast. But just as 3 Mars orbiters prepared to capture the flyby, their live feeds went dark, one after another. The silence was total. No images, no telemetry, just static on every channel. In that darkness, one truth whispered through the static: something had outrun the stars. For the next few hours, Mars slept under a sky no one could explain, and when the data returned, part of it was simply gone. Maybe a glitch, maybe coincidence, but space doesn't make mistakes that easily. Something outran the stars, and the data disappeared. From that night, the mystery began. The story didn't end with silence, it began with one man who refused to look away. Stephen Burns, an amateur astronomer known for his precision and restraint, spent nights combing through Perseverance's raw image archives, frame by frame. He searched for what others had dismissed as noise. He stacked the frames, aligning the background stars until the faint streak revealed itself razor thin, unwavering, cutting across the Martian sky like a scar of light. Then he went further. He calibrated the plate scale using known star separations, checked each timestamp against rover telemetry, ruling out cosmic rays and fixed camera ghosts. Every test he ran pointed to the same impossible truth. The streak was real. Its velocity 60 kilometers per second. Consistent. Measured. Verified. At Mars distance. No meteor. No satellite. No cosmic ray could behave like that. And in the quiet of his small observatory, Burns whispered the line that would ignite a global debate at Mars's distance. 60 kilometers per second can only belong to one class of travelers, the interstellar kind. When Burns released the time-lapse, it spread like wildfire. Within hours, tens of thousands had downloaded the Perseverance frames, determined to prove him right or prove him wrong. Across astronomy forums and open source labs, people began stacking, filtering, realigning. Some claim to see it again a second streak. Smaller, faster, vanishing halfway through the sequence. Others saw nothing but static. To them, it was all noise, random cosmic rays stitched into illusion. Then, at exactly 0003 UTC, someone noticed a single frame flare, a faint green flash that lasted less than a second. The community erupted. Was it chemistry? Or compression? A real emission line, or just a cosmic ray striking the sensor? Threads filled with arguments about color channels, filter calibration, overstacking, understacking. Everyone had data. No one had proof. Without the original FITS files, the uncompressed raw format, every claim was provisional. Everyone was chasing ghosts through compression. And somewhere in that blur of pixels and passion, one question lingered in every mind. What if the ghost was real, while Earth's telescopes were blinded by the sun? Mars became humanity's best window into the mystery. 3 orbiters were reassigned from their routine planetary scans to a single, fleeting objective to capture 3I Atlas during its historic flyby. The Mars Reconnaissance Orbiter, with its HiRISE camera, was chosen for high-resolution imaging sharp enough to spot boulders on Martian slopes. The ESA Trace Gas Orbiter, equipped with the CaSSIS spectrometer, prepared to scan for color shifts and chemical signatures, and the veteran Mars Express, carrying the HRSC wide-angle imager, would sweep the sky for broader structural patterns, tails, fragments, or desplumes. But the challenge was almost absurd. The object was 9 million kilometers away, about 75 times the distance between Earth and the Moon. At that range, even HiRISE, humanity's sharpest eye on Mars, could resolve no more than dozens of kilometers per pixel. For the first time, the orbiters were reprogrammed to chase a moving target, no real-time tracking, just pre-calculated gambles in the dark. Each exposure had to lead the object's predicted path by seconds, hoping it would cross the field of view at the exact right moment. Too early, and it would be out of frame. Too late, and it would vanish into the stars. Every shot was a bet, a roll of cosmic dice against time, light, and the limits of human precision. Normally, Mars data goes public within 3 to 5 days, quick look images first. Then the raw FITS files for anyone to analyze. This time, nothing. No previews, no downloads, not even a confirmation the data existed. Days passed. The discussion boards went quiet. The forums turned restless. People began to ask whether NASA or ESA had decided to hold the images back. Inside JPL, the imaging teams described the delay not as secrecy but survival. Every misaligned pixel could ignite a global frenzy. For fast-moving targets like 3I Atlas, the standard correction pipelines break down. Even cosmic ray filters tuned for slow Martian landscapes fail to separate real signals from stray particles. Releasing a single unverified frame could spark chaos, a digital ghost mistaken for discovery. So the teams checked everything, frame by frame, line by line, knowing that every pixel carried the weight of credibility. In science, caution can look like silence. And so, while the world waited for answers, Mars spoke only in static. The first spectra from Mars Express and TGO finally arrived, faint, incomplete, but enough to light a fuse in the scientific community. Normally, a comet's green glow comes from diatomic carbon when sunlight breaks the bond between carbon atoms, releasing light at 516 and 563 nanometers. It's so reliable that astronomers call it the swan signature, the chemical fingerprint of every active comet. But 3I Atlas broke the rule. Its spectrum showed a strong green emission, but the swan bands were missing. No diatomic carbon. No C2 pattern. Instead, the data revealed an atmosphere rich in carbon dioxide, flooded with volatile gases, but strangely poor in classic carbon chains. For comet scientists, that's not just unusual, it's impossible. A green glow without diatomic carbon chemistry with no name. And somewhere in those missing bands lies a question no instrument can yet answer: what exactly is 3I Atlas made of, as the analysis deepened. Another anomaly surfaced this time. In the metallic spectrum, the Mars Express data revealed something unseen in ordinary comets, nickel lines dominating the chart. While iron remained faint and almost silent, in our solar system, it's always the opposite. Iron sings louder. Nickel hides in the background. But here, the element balance was inverted, breaking one of comet science's oldest expectations. The gas composition added to the mystery. Carbon dioxide outgassing was nearly 10 times stronger than water, a chemical imbalance that defied solar heating models. For an object so close to the Sun, water should lead. But 3I Atlas refused to follow that rule. Its mass and thermal profile painted a contradiction: too heavy to be dust, too cold to be rock, a body too cold for its chemistry. Too heavy for its tail? The first clear images from the Mars orbiters revealed something no one expected: a tail that pointed the wrong way. Instead of streaming away from the Sun. 3. Atlas threw its jet directly toward it, an anti-tail. Sharp and unnaturally bright. The brightness gradient dropped off like a cliff, the edge defined as if cut by a laser. Dynamic models struggled to explain it. A jet facing the Sun should push the comet off course, yet 3I Atlas stayed perfectly stable, even with visible jets. No non-gravitational acceleration was detected. Its orbit stayed perfectly clean, as if mass itself refused to move. Astronomers recalculated again and again, searching for a hidden correction, a flaw, anything that made sense. Nothing did. 10 billion tons and silence. While scientists debated the chemistry, one research group, Vibe Labs, looked at the sky from a different angle. They traced 3I Atlas backward through decades of orbital simulations, asking a question few dared to ask: where had it come from? The result froze the room. The path intersected a tiny region of sky, the same coordinates as the famous 1977. Wow! Signal. The frequency of that signal, 1420 MHz, the hydrogen line, nature's universal language. The hydrogen line, nature's universal language, where the universe once whispered back. The statistical overlap, just 0.6%. Small, but not zero. Coincidence or choreography across 50 years as October turned to November. 3. Atlas slipped behind the Sun into the one place no telescope can follow. For 5 weeks, every eye, Earth and Mars alike, goes blind. No signals, no reflections, just silence. Stretching across space, in that blindness, the story waits. As 3I Atlas hides behind the Sun, the world waits for its return and for answers. Astronomers prepare their watch list 4 signs that could change everything once the object re-emerges. First, brightness. A shift in magnitude greater than 1 could mean fragmentation or flare. Second, trajectory. Even a deviation of 0.05 degrees could suggest non-gravitational forces. Third, jet morphology. Will it show another anti-tail, or return to a normal outgassing plume? Fourth, spectral ratio, the balance of nickel, carbon dioxide, and water, the fingerprint of its changing chemistry. Every anomaly must climb the ladder from repeatability to multiband proof to dynamic geometry to intent. The higher it climbs, the louder it speaks. If any of these change, the mystery deepens. Maybe it's just ice and dust torn from a forgotten world. Or maybe it's a mirror reflecting how little we truly understand. For now, we hold a stack of anomalies waiting for the universe to explain itself. When the images arrive, we'll decode the light